Hello and welcome to another episode of the Clojure Appeals screencast. This is episode number 18 and we are going to talk about fold. Before we start, a quick mention of the book I'm writing for Manning. The content of this screencast is based on the content of the book. You can get a 42% discount at checkout with the code that is displayed on the slide. The website for the book is also displayed on the slide below. And @reborg is my Twitter handle if you want to get in touch or if you have any question. There's also something new about the book. Manning made available the book as a browsable live book experience, so you can now access the book online and you can easily follow links, and there are many in this kind of reference book. So if you are on a function and is mentioning other function, you can quickly follow them by just clicking around. All right, let's get started. Fold is the entry point in the Clojure Standard Library for the fork join framework that is available since JDK 1.7. Fold is potentially a parallel operation. It's on the surface quite similar to reduce, but it has many knobs that we can use to parameterize the parallel computation that we're going to see in this episode. The doc string is quite verbose. There's a lot to say about fold, but I think the most important parts are that based on this fork join framework, Clojure designed fold to be a reduce combine function. So many reduce operations that are going to apply some processing to data are going to execute on a smaller chunk of the initial collection, as I said, in parallel, and they're going to be combined back into the final result. And the combination, when these results are the chunks are combined back, this operation needs to be associative because the combination can happen in any order. So that's one thing to take into account when you use combinef. So let's now have a look at some examples. You need to require the reducer namespace to use anything fold related, including reducers. We are going to see the relationship between fold and reducers in a second. So as I said, it's quite like reduce. So this is a simple reduce with plus over 1000 numbers. And you can, of course, do any kind of processing before that. You can map, you can filter, and that's the usual thing. But fold has this secret weapon available. So if we now try to run fold on a normal sequence, lazy sequence in this case, a range, we can see that it's taking some time, mostly to create the range. If we use it on a vector instead, it's going to take less time. So this is a very simple example. It's still showing an improvement, an increase. It's not a very formal performance benchmark, but it's giving you an idea. And the second example is using a vector instead of a normal range. And that is what is triggering the parallelism for fold. So vectors and maps are hash maps are parallel enabled. So how does it work? I prepared a little diagram here. So the initial collection, when it's a vectors or a hash map, is split into chunks of a certain size. And these chunks are assigned to fork join tasks, and you can create as many as you want. And they are not, there's no one-to-one relationship between tasks and threads. And the fork join frameworks will will organize the tasks so they are assigned to the available threads. And there are, depending how many cores you have, there are 4 cores, for example, for this computer. And the tasks are then assigned to those threads and executed. When the task is finished, the combine function will combine the results back together into the final assembled result. One important thing to remember about the fork join framework is that it enables work stealing. So if a thread is not busy while another one instead is doing a lot of work, then that thread can steal the job or many more jobs from the queue of another thread and execute them itself. So it is keeping all the available threads quite busy. So let's go back to the example. Let's see what else we need to know. So fork join or reduce combine fit nicely to do processing on data at leaf. By leaf, I mean when a chunk is being, when a collection is being split into chunk, and this chunk is executed on a single core. That is a leaf, and all the processing should hopefully happen at that point because that will be processing that is happening in parallel. Um, we can see here that if I just take a vector, which is a fold enabled or a foldable type, and I do some processing on it, this is not executing at the leaf. So the fold is not going in parallel in this case because mapping and filtering are generating another sequence on top of the vector, and the fold cannot execute in parallel. And to confirm that, I added an identity map operation that is just printing the current thread, and we can see that each operation is executing on the main thread. What instead should happen is that the thread that is executing the operation is a fork join pull thread, as you can see in this other example. And what changed here is that we gave the possibility to the processing to happen at the leaf. In order to do that, we need to use reducers, which are also part of the same namespace. So as you can see here, I prepended r/ to map filter and the second map operation, and that is propagating essentially the vector type up to fold, and is also making sure that the foldable collection is seen by fold and the operation can happen in parallel. So it is in this case not sequential, and you can see it from what the thread are printing. So if you want to do this processing at the leaf with fold, you need to use reducers to enable that. We're going to see in a second that you can also use transducers. There are a few things to keep in mind when you do that, but let's go in order. So you have additional knobs, as I was saying, to decide what to do with the parallel computation. For instance, you can decide to have a reduce function, which is different from the combine function, so they can be independent. In this case, I have a divide by operation as the reducing operation, and a multiplication as the combine operation. So it's just generating a very large number, but you get the idea. We're going to see an example in a second. It is more complete and is showing you why sometimes you might need to have combinef and reducef as different functions. You can also decide the desired chunk size. So by default, it's going to be 512. What does it mean is that the fork join framework will try to keep the chunk size to 512 elements unless you give another chunk size. Not the fork join framework. In this case, is the implementation of fold. And is a desired chunk size because sometimes, of course, depending on the size of the collection, you cannot have perfect chunks all the same of a given amount of elements. So it will roughly try to maintain that. So in this case, I just executed a fold where the chunk size is 400 instead of 512. Nothing is changing really. The reason why you want to change the chunk size is related to the kind of computation you are executing, to the complexity of the processing that you need. So the length of each task can decide that, the length of how much big is the collection, and so on. Let's also have a look at in which way fold is deciding what is the initial element for the reduce. So you know that a reduce operation needs to start from some element. If you don't pass any initial element in normal reduce, the initial element will be the first element in the collection. But with fold, you'll have to be more explicit about that. And the way fold works is that it's gonna use either reducef or combineth, and it's going to call the singularity of one of them, sorry, the zeroarity of one of them to decide which is the initial value. So in this case, for example, that I only have reducive, I just commented out, we can see that it's printing init 0. It means that it's using the number 0 to initialize each reduce operation that happens at the leaf. But if I pass also the combineth function, that takes precedence. So the zeroarity of the combineth function is deciding what is the initial value. In this case, minus 500. Let me see what else. Okay, so since this is quite often the case that you need a zeroarity function to decide what is the initial value, there is a helper in the reducers library called monoid that's taking two arguments, and the first one is going to be the actual combineth, the actual combination or reducing function, and the second one is the initial value, in this case a function of no argument. So constantly will definitely do the trick. And this operation that I just executed is exactly the same as before, but we're using monoid in order to avoid to explicitly write a zeroarity and twoarity functions every time. And one last detail to take into account is that when you're not using vectors as the initial input, but you're using hashmap, then the reduce function is similar to reduce kv. So it's a function of 3 arguments, not 2 arguments. And like reduce kv, the first argument is the map, the second is the key, and the third is the value. So in this case, I'm creating a hash map, and I'm transforming each value to a string using a reduce function of 3 arguments, as expected, and I'm using merge to combine every single smaller map into the final result, which is the larger map. All right, so I wanted to show you how you can use, one way you can use a fold, and this is a typical case of word counting word frequencies. And we have here, let's start from the bottom. What I want to be able to do is to grab some large chunk of text and split it into words and then count the frequency of each word. We can do this in parallel quite easily with fold. So the example starts by fetching frequencies from a large text. The Gutenberg library contains several plain text books. One of them is War and Peace, which is one of the largest. And I'm slurping that and split everything into words. Then I'm passing these frequencies, I'm passing this long collection of words to this words function that is just a wrapper for a fold. And the fold is using a combineth and a reduceth that you can see in the left here at the top. And the first operation that it does is taking each word and producing a pair or a tuple for each word, where the word is the first element in the tuple and the second element is just the number 1. And this is an easy way then to sum up the frequencies for each word, because we have the number 1 here that can be summed up to other number 1s that are for the same word in other places. And indeed, the reduce function that we can see here is doing assocking the key, which is the word, to the map that is going to be produced increasingly, and is doing an assoc of 0 if it's the first time we see the word, or it's summing up the already present value, which is the counter, to the number 1, which is present in each tuple if the word was already seen before. Combineth is merging all the chunks, and in this case each chunk is a map, back together in a larger map. And in order to do that, we merge it, and we merge with plus. Of course, because we are probably going to find the same word in multiple chunks, and we just want to have the word summed up in the final results. We're using monoid, as explained before, and the initial value for each chunk the map is the empty map. So I just remember now that I don't have an internet connection at the moment. Um, well, you'll have to trust me on this one because I have the file locally somewhere, but it might just take me uh, too much time and too much trouble to put it into working condition now. So trust me on this one, or if you go to the show notes, you can just execute this code, and you should see at the end that if you take the most frequent words at the end, you will see that it's working as expected. So let's have a look now at what are the possible problems you can have when you use fold and reducers. First of all, there is a small subset of the reducers available in the reducers namespace, namely drop, take, and take while, that are not foldable, meaning that if you use them, like in this case, in this example with a drop 0, which is doing essentially nothing, it will prevent parallelism. And there are multiple reasons for this to be the case. One is that they are stateful, so they contain some state in order to work properly. And in order to run in a parallel concurrent environment, these states need to be protected. And this is not something that they are doing out of the box. And the other thing is also that while drop, take, and take while have a perfectly fine semantic on sequential collections, like drop is saying drop n elements from the beginning of the collection, not the middle, not the end of the collection. It requires a different semantic when they run in parallel. So we can assume, or we can agree that drop is going to drop n elements from each chunk in the collection and then is combined back. But we need to agree on that, and also, probably more importantly, is that the results of using drop in a concurrent parallel environment is going to be different from using the same drop operation on a normal sequential operation. So for these reasons, drop, take, and take while are not foldable. And we can see, we can run this. It's not visible now, but if we take the map that we used at the beginning, this one, and we go all the way down so I can show you, and we'll just stick it here, we should see that this is running on the main thread instead of running on the fork join thread. So be careful if you use any of those reducers. Fold will suddenly stop to go in parallel. You might have problems with that or not, depending on the kind of operation you're doing. And I did actually a bad thing. So now I'm going to kill and restart the REPL, and we'll take it from here. So let me just require again the transducers. And let's go back. And we are here. So we just show what happens if you use drop. And what is the relationship with transducers, by the way? So they are very connected. So essentially reducers and transducers are different implementation of the same principle, if you wish. And so you can move between them by just calling the reducing operation on the composition of the transducers. When you do that, you essentially obtain the reducing function that can be used by fold or reduce or any other operation that requires a reducing function on any on any possible collection. Of course, if you use it with fold, so if you use your chain of transducers here, you call it on the reducing function that you want, and you use it with fold on a vector, this operation will go parallel. So one possible way to use transducers in parallel is to go with fold. There are other ways of doing transducers in parallel. One is to use pipelines with core async. that's perfectly fine as well. Um, but you need to be careful again, because while reducers are, are, are explicitly preventing you to go parallel and to create problems, so they're going sequential. With transducers, this is not happening. So you are free to use a drop operation as a transducer operation, but if you do that, you might see unexpected results. For example, in this case, the drop transducers, which is a stateful transducer, is used in parallel, and the concurrency is, of course, creating contention. So threads are able to read a value of the counter that is inside the drop that is different because some other threads came in before and executed the reducing step and decremented that counter. So essentially what I want to say is that if you execute this fold operation many times, like I'm doing here, which is exactly the same, and you take the distance, you should see one results only. And instead we are seeing many more. And the reason is that uh, the dropping operation is dropping less or more elements than expected on each chunk because of the concurrent threads executing the state inside the drop. There is a way to get around that I documented in this gist. Uh, uh, I'm not able to show you what is in there because it's quite long and it's a little bit tricky, but I explained how it works there, and you can use stateful transducers in a parallel context by using this trick. Another interesting thing to discuss is how it compares to PMAP. Um, so the two are essentially completely different models of execution, of parallel execution of tasks. And they both have strengths and they both have very good use cases. So one does not include the other. They actually kind of very nicely complement each other. So pmap is definitely where you want to go if you care about laziness. You want to load the entire input collection in memory at once, while fold definitely will do that. Pmap is also going to execute, if you use it on a vector, is also going to use many more concurrent threads. So that could be an advantage or not, depending on the amount of contention those threads are generating. And the fold, of course, has the fork join framework behind. That means it's going to prevent work stealing. So it's going to work better if tasks are unpredictable, while instead pmap, especially in lazy sequences, will suffer if the task length is very different. And I prepared an example to highlight this fact. So I'm going to use a visual VM connected to the repo, and because it's got like a pretty decent visualization of the threads that are running at any given point. So if you have a look at this graph of green and yellow bars, in a second you will see what happens when I'm executing. So I'll make this window uh, smaller so we can see the threads here running and their names, so we can see where they're running. So I prepared, oops, sorry, I prepared an example. Here it is. I prepared an example which is essentially some processing that happens on a collection. And this processing, to make it real processing, I created this pi function that is calculating pi using the Newton method. I'm not sure 100%. Is using a mathematical method to approximate pi. And the bigger is this number here, n, the better is the approximation for pi that is going to produce. And for numbers like around 3000, like I have here, it starts to be quite a long computation, an intensive computation. So what I'm doing here in this assorted tasks collection is that I'm giving about 90% of tasks that are very small, very quick to execute, and 10 tasks that are instead quite large and much more difficult to execute. So it's a sorted task in that sense. Some of them are easily predictable, they are quite short. Others are not predictable, they're going to take much more longer time. So let's see how pmap will compare to fold in this case. And I have here a way to run the pmap. The pmap has this a function of one argument, which is destructuring an index, which is just an incremental index, and the time t to pass to the pi function down here in order to make it more or less long, more or less computational intensive. This clock here is just a trick so I can have the last thread to execute to calculate the elapsed time. So if we run this, we can see on this side, hopefully, um, oops, yes, there was a problem here that I didn't see. The clock is not, oh yes, I'm sorry, I have to evaluate all the rest before. So we should see on this side, on the other side, that some threads are created. And unfortunately they are not ordered, but they are created okay. Let me see if I can put them down. So these are created are all the threads here with Clojure agent send off pool. And as you can see, while they are executing uh, 6 at a time. And some of them are always green, some others are constantly brownish orange. And this is telling us that some of them are running longer tasks, while others need to wait until the task finishes. And this is the way pmap will work on a lazy sequence. It's going to use number cores plus 2 threads. In my case, it's 4 plus 2. So we're going to see 6 things here running at any given time. If we use a fold for the same operation, we'll see that is executing in a much different way. So first of all, we only have 4 workers, 1 for each core, and each of these workers is nicely busy, meaning that if there is any task that is taking longer than if there was any task for that thread waiting, another thread is taking care of that, is stealing the job and executing it on their own context. And you can see how faster this is executing is taking yeah, almost half the time to execute. So this is, of course, making is an illustrational example to show you what happens. So you might not have this in real life. But I suggest to do something similar if you have some parallel problem that you want to solve and you are not sure if this is a problem that you can solve with pmap or you can solve with fold, is to take a tool like a Visual VM Connect to the REPL or the running application and see what's going on there and decide after which of the two models is serving you the best. In general, if you have lazy sequences, probably pmap, sorry, if you want to maintain laziness, pmap is your only way to go. If you don't care a lot about laziness, then you might want to look at the predictability of the tasks. If they are all nicely the same, roughly the same size, roughly the same elapsed time to calculate, then pmap might still serve you quite well. If instead they are unpredictable, maybe fold is a better solution. And then, of course, there is also some reasoning to do about the way you use pmap, the way you use fold, especially with transducers, where you can compose a lot of operations in a nice processing pipeline, which can be reused in many places. So there are all these considerations to be done between fold and pmap. If you look at the show notes, I have a few more interesting examples down here. You can see some other examples that I found, but it's like an extension to this screencast that is going to be long anyway, so I'm not going to go through them right now. But I think you got the general message about parallelism with fold, I hope. So I think that was all I wanted to say to you regarding Fold. So the show notes are available on the Clojure Peel's GitHub project that you can see on the slide. And as usual, thanks for listening, and until the next time, goodbye.